Cool. Thanks, Tony. Okay, well, good afternoon, everybody. Thank you so much for joining us. Like Tony said, we are the Master's Project team from the University of Michigan, and this is our capstone project that we've been working on for the past year and a half. Um, Before we dive in, we wanted to acknowledge all of the folks who've contributed either directly or indirectly to this work. The last 18 months would not be possible without their support. And once again, we are honored for the opportunity to assist BNGA in this work and thankful for the trust placed in us. This is our C's team. So my name is Mary Kelly. I'm a geospatial data sciences master's student. We also have on the call Lou Buller, also a GDS student. Bridget Hennessy and Gus Ridding are GDS and ecosystem science and management students. And then we also have Maya Keeson, who is our environmental justice and environmental policy and planning specialist. Okay, I think this is Lou's slide.
Yep, so this was our slide kind of introducing BNGA for when we presented this at school, but it looks like this audience is going to be mostly already familiar with that. So this was just to talk about how we kind of co-produced this project with people we talked with, like Tony mostly, and Sean, and people we met at with the Rocky Boy Bison program and the Natural Resources Department out at Rocky Boy. When we did our field work, we got to talk to a lot of people, and that kind of informed all the work that we did in this project. Um, and then we can move on. So this is kind of a flow chart of the different components of our project. It had 5 of us doing a lot of different things. So this kind of largest component of the project was focused on ecological connectivity. So the BNGA's kind of project proposal had indicated they had some interest in tools for geospatial analysis of connectivity. So we started with some background research into the existing software tools. And then I did some systematic literature review search for relevant examples of connectivity analysis. And then there's very few examples from the Northern Great Plains doing this kind of connectivity analysis. It seems like a lot of that research has been more focused it on forested biomes, so there's kind of a gap in the research there. And the starting point for working with a lot of those tools was this description of like where the habitat is. So a lot of our work and our deliverables for this component of the project are part of this assessing habitat suitability. We discussed with Tony kind of what BNGA's priorities and potential applications might be and whether we should focus on a particular species for our connectivity work. And we decided to focus on pronghorn. So then we did find a good example to build off of with. So our goal was to use that as an example to help BNGA develop sort of a reproducible workflow for connectivity analysis in the future. So something they could adapt to other priority species potentially. And so we found a good example to work off of for geospatial analysis of like pronghorn habitat connectivity. But it was from a while ago and from a different area. So we're going to be working with the exact same data. So the first kind of deliverable, and that's what Mary's going to talk about in a bit, was the ground truthing to kind of find out what geospatial data sets were going to be accurate in our study area. And then Bridget will talk more about the other deliverable, which was related to the habitat suitability and connectivity analysis part. And then there are kind of 2 other components of the project. For the second component, Gus worked on some models to automate mapping of bison activity by using remote sensing and machine learning to detect the impacts of bison on the landscape. And we're hoping that that sort of monitoring could be useful to like tribal bison programs and kind of supporting BNGA's work in that area. And then for the policy component of our project, that was related to this North American Grasslands Conservation Act and sort of BNGA's goals of increasing Indigenous-led management in the Northern Great Plains. So Maya's going to talk about that part of the work, developing a tool to explore financing strategy options and present some recommendations to make NAGCA more attractive to Congress. So that's kind of the overview of the project, and we can go on to the next set of slides that are talking about this pronghorn habitat suitability component.
Yeah. Okay, so to do the pronghorn habitat assessment that Bridget's going to talk about in a moment, you need input data to go into that model. And so we decided to use open source or freely available data sets to avoid asking BNGA or their partners for information. We're trying to avoid sort of extractive research practices. And the choice of what data sets to use, like Lou mentioned, was informed by a literature review focused on habitat variables relevant to pronghorn. What types of landscapes do they gravitate towards? Things like that. And generally, it's a good idea when you're developing this kind of model to verify the accuracy of your data um, to ensure that your model is reliable. So the main way that we do that is through ground truthing, which is this validation of our reference data using on-the-ground observations. So actually going out into the field and making sure that what the data set says is there is actually there. And the goal of this ground truthing effort is to determine what variables BNGA should measure when doing future connectivity analyses. And so we went to Montana, to Rocky Boy, and we collected 392 GPS points and 55 lines using our phones that were connected to some GPS units via Bluetooth. And you can see all of those on the map here. And that was done over 5 days in the field. So we took all of those points and lines over about a week. And then and it looked kind of something like this, where we have a measuring tape and our GPS units and our phones, and we're just sort of taking points every 10 meters. And then when we returned to Michigan, we did sort of that validation piece to determine how well our field data matched up with those reference data sets. So those variables included things like elevation, which we have on the slide here, as well as vegetation height, I guess estimated vegetation height in meters, vegetation cover, so the percent vegetation cover in the different areas, um, vegetation communities. We have kind of a bar chart here because mapping them would be quite an effort. There's around 50 different vegetation communities, so limiting them to 10 works well for this graph purposes. We also looked at roads, so some US Census Bureau roads data contrasted with our ground truth roads, soil data, and then the last thing was land cover, so things like agriculture, forest, grassland, things like that. And from all of this, we made recommendations to BNGA about what data sets to use for future analyses, which are the first thing we recommend is to collect more points. So we collected around 392 points. We recommend sort of a larger sample size than that to compare the accuracy a little bit better. It makes things a little bit easier. We also recommend maybe generating a set of random points in GIS, Geographic Information Systems, sort of your mapping software beforehand, and then visiting those sites in the field. We did not do that. We just kind of went into the field and picked random areas, sort of a visual inspection, and adapted our sampling strategy as we went. So generating sort of those set random points would be a more efficient use of time and also reduce bias if you have any bias in the distribution of your sampling sites. For the data sets themselves, they all sort of have varying accuracy. So we found that for low elevation areas, either of the digital elevation models that we looked at could work well. The vegetation cover, vegetation height, vegetation type, this land fire data, we would caution against it since it has kind of a lower accuracy. The roads did fairly well, so we do recommend the roads data. They were around 61% matching in terms of their location. The soils data was great, highly accurate at around 96%. And then this last one, the cropland data layer, the 10 meter or the 30 meter could work well, depending on your computing power and how much space you have on your computer for working with that amount of data. Um, that particular layer performed much better than the land fire data. So we do recommend that data set moving forward. The last part is sort of just generally streamlining the workflow. We recommend collecting all of the different variables at every single point to avoid gaps in the data. We had a few areas where we were missing some variables at different points, which contributed to gaps and may have impacted our accuracy analysis a little bit. And then another option could be if you have Python skills, to maybe automate a bit of this data validation using like a Python script or an R script, since a lot of these error calculations are pretty consistent and pretty similar across data sets. And just sort of doing all that automation all at once would speed things up. Okay, I'll hand it off to Bridget to talk about the habitat assessment.
Thanks. Hi, everyone. So as Mary was saying, the ground truthing results led into what data to use for this pronghorn habitat assessment. In our talks with Tony, we decided to focus on pronghorn as they are an indicator species, meaning that their population health and dynamics can indicate overall grassland health and grassland dynamics. So by assessing their ecological connectivity, we can kind of gain insight into overall grassland health. There are different components under the term ecological connectivity. Structural and functional are two that we use to answer our research questions, which were one, what connectivity metrics can derive meaningful information about grassland connectivity in the NGP ecoregion? So for this, we looked at structural connectivity, which is the physical arrangement and configuration of the habitat of interest, which for pronghorn is primarily grassland. And then our second question was, what is the state of pronghorn habitability in Rocky Boys Reservation based on the connectivity tool used, and what areas should be prioritized for restoration? For this, we looked at functional connectivity, which focuses more on like actual species habitat preferences and how the animal or pronghorn actually kind of use and move through the landscape. Our study area was focused on Rocky Boys Reservation. So throughout the analysis, we expanded it to the surrounding counties of Hill and Chouteau to kind of be able to compare Rocky Boys connectivity to those areas and get perspective into how grassland is shaped throughout the entire landscape. Okay, so for our structural connectivity, where we were trying to answer overall grassland connectivity, as a brief intro, structural connectivity describes the physical arrangement of grassland on a map. So it could form like large contiguous areas of grassland or be more broken up due to intersection with other land cover types. So kind of in this idea, each grassland patch is like its own island, and it can be close to other islands or connected by bridges or be shaped irregularly. And for our methods, we calculated different metrics of the grassland patches over our study area. And here are some examples of some of the metrics we looked at. So this purple diagram is showing perimeter to area ratio, which is a comparison of how much perimeter there is to the patch's area. A lower ratio is better because it means that the patch is kind of regularly shaped and hasn't been experiencing loss of habitat or fragmentation. Edge density is this green diagram. It's kind of similar to perimeter area ratio, but it's looking at the amount of kind of patch edge compared to the entire landscape. So the amount of transitions that a species would have to go through across the entire landscape. A low edge density is good because it means less boundaries to cross, which usually indicates less broken up patches. And this green diagram can also show another metric, number of patches, which is just a count of how many contiguous patches or islands of grassland that there are. So a lower number of patches is good, because it indicates that the patches haven't been broken up into smaller and smaller areas. And then patch density is this top red figure. It's similar to number of patches, but it equals the number of patches per the size of the area. So a higher patch density is bad. It means that there are a lot of broken up habitats in the area. And then patch cohesion is this last one, this lower red figure. It's how physically connected or clumped up a patch is to itself. Higher patch cohesion means that the patch does not have like little perforations that could grow into complete divisions in the patch. And landscapes with high structural connectivity and high ecological connectivity would have a low perimeter to area ratio, low edge density, low number of patches, low patch density, and high patch cohesion. And all of this would signal like nice connectivity in the region. So when we analyzed our results of these metrics, we unfortunately found many indications of more grassland fragmentation in Rocky Boy compared to the surrounding counties of Hill and Chouteau. The grassland patches in the reservation were smaller and more broken up and overall farther away from each other. But as a good sign, we also found that the grassland patches in Rocky Boy were like normally shaped, well aggregated, and not interspersed or perforated with other land cover types, which was a good sign. And then we also found 4 large grassland patches in the reservation that exceed pronghorn habitat size requirements. So enough grassland area to live, feed, reproduce on, which is the next figure, Mary. Thank you. So yeah, these are the 4 large patches that we found. However, there are some limitations to our study. Our findings could be due to the overall complex shape of Rocky Boy. We used geographical boundaries to split up the 3 study areas of the reservation and the 2 counties. And these boundaries might not actually be true like on the ground for the pronghorn. So we may have been artificially dividing grassland patches that are contiguous in the eyes of the animal. So this next figure is example of patches that are connected to each other through grassland in the surrounding counties without these kind of territorial boundaries imposed. And then, so when we looked without boundaries, which is our next figure, we imposed instead a 12.9-mile buffer area around the reservation, which is the average maximum daily movement amount for pronghorn. And we found that the 4 patches that we identified were connected to each other and connected to this huge area of grassland that spans quite far. So we were correct that when not imposing boundaries, that the grassland is pretty connected. Additionally, our findings could be due to overall size differences. Rocky Boys Reservation has like a much smaller area than Hill and Chouteau County, and it has the smallest ratio of grassland, which I think is the next figure. So it kind of follows that some of our non-standardized metrics that we were looking at that don't account for overall area are finding smaller grassland patches, which indicates fragmentation. And then when we move on to our functional connectivity assessment, where we were trying to answer the question of suitability of the land for pronghorn, we borrowed a weighting system from a different pronghorn study to create a habitat suitability map, which was based off of species habitat preferences of 5 variables. We looked at land cover type, forage quality or NDVI, topographic position, distance to roads, and distance to water. In this weighting system, land cover is like the most important variable for pronghorn. And then within that category, there are also sub-weights applied to the different land cover types. So pronghorn primarily prefer shrublands and grasslands, which in this weighting system are the highest. And then the developed land is like the least suitable habitat. So you can kind of see in the weighting system how that plays out. And then that follows for all the other variables. So if we look at our least important variable, the lowest weighted variable, distance to water, pronghorn prefer to be closer to water than farther to water, but it's weighted as like the least heavy variable because they get a lot of their water from their forage. And then each pixel of the map is assessed according to these variables, and the weights are multiplied together, and we get this habitat suitability map, which is the next figure. So the highest value areas from the weighting system are the most suitable, and those are like the green, dark green areas on this map. And then when we kind of zoom in to just Rocky Boys Reservation and their suitability, we see many areas that show high suitability there, which is the darkest green. Though these areas are kind of concentrated near the borders of the reservation. So we think future studies could examine whether there are barriers to movement around these areas to the surrounding counties, which would kind of limit pronghorn presence in the reservation or make it kind of difficult to get to these suitable areas. And then this study also kind of had some limitations. We didn't have actual pronghorn location data to see where pronghorn actually go or see their movement patterns, which would verify the suitability of the land. And then additionally, the study we were modeling after didn't have forest in their study area, whereas Rocky Boy is pretty forested in like the southeast corner. So when you look at this map, you can kind of see there's like a lack of data down there. There's not as much color due to the forest not translating well. And then for our recommendations from this part of the study, we think that monitoring the 4 large patches found that we should monitor them to make sure they remain connected to the grassland and the surrounding landscape, and overall monitor the structural connectivity metrics for like huge changes in size and shape, which would forecast future divisions in the grassland and forecast fragmentation. And then for our functional assessment, we recommend to examine barriers to movement along the areas of high suitability, and then if possible, procure pronghorn location data to verify where pronghorn are and their movement patterns. And then an overall recommendation would be to use wildlife-friendly fencing when possible to kind of ease their movement in the landscape. And then moving on, another species we focused on is bison, which Gus will talk about.
Thank you, Bridget. So this project really starts from a practical challenge. BNGA works across many native nations in the Northern Great Plains, and one of the key goals is restoring relationships between people, land, and species like bison. Monitoring what's actually happening on the ground across large areas can be difficult, it's time intensive, and it's also expensive. So the purpose of this project is to explore whether artificial intelligence can help with that. And more specifically, I looked at whether AI can be used to detect signs of ecological activity, and particularly bison disturbance. In this way, it can be scalable, efficient, and useful for decision making in the future. For why bison and wallowing, I focused on bison because they play a central role in both ecology and culture in the Northern Great Plains. Within 16 native nations supported by BNGA, 14 have bison programs, and across the United States, more than half of bison and conservation herds are managed by indigenous people. Bison are considered a keystone species and an ecosystem engineer, meaning their behavior shapes the landscape. And one of the most visible ways they do this is through wallowing, when they roll and create depressions on the ground. These wallows are important because they create small habitats for plants and insects, they hold water and increase landscape variability, and they help prevent invasive species. Because of this, wallows can act as a kind of indicator of ecosystem function. So if we detect where wallowing is happening, we can start to understand where bison are actively shaping the land. The problem is that wallows are pretty hard to measure. Traditional methods like field surveys or manually reviewing aerial imagery takes a lot of time and resources, and they don't really scale well across different kinds of landscapes. So this project asks 3 main questions. Can AI help automate that process? And the 3 questions that were asked were, can AI accurately detect bison wallows from high resolution imagery? What are the limitations of using AI for this type of detection? And how can information support restoration and management decisions? To answer these questions, I worked with data from 2 main locations, the Rocky Boy Buffalo Project in Rocky Boys Reservation, Montana, and existing data set from the Konza Prairie Biological Station in Kansas. There wasn't enough field data collected in Montana alone, so I used the Kansas data set to train the models and then applied them to Rocky Boy. I also used aerial imagery from National Aerial Imagery Program, which provides high resolution imagery that can be both visible and infrared. So I used 2 different types of AI models. The first is deep learning, which looks for patterns in both shape and color and detect objects. In this case, I conducted deep learning through the ArcGIS Deep Learning Toolkit, which essentially is a black box of inputs and outputs. And we created a raster stack from the many different layers that we used for ground truthing in this literature to define where wallowing was occurring. For example, this is normal color, infrared, PCA, distance accumulation raster, and a DEM. The first step in the model evaluation looks something like this, where if you go to the net, where you select chips and identify where wallowing has occurred. So this is where we use the research available to us to identify ground truth wallows. And the next step in model evaluation looks something like this, where the best fit architecture for the model is selected. like I said, the ArcGIS Deep Learning Toolkit is kind of a black box. So by throwing it in here, it performs this calculation for us, and we have to run it again, which gives us a better understanding of the precision and how we can use and the how this model is used and how it will perform as an object detection model. So after conferring with professors, we thought that a machine learning route called random forest, which classifies pixels based on their spectral values, might be a better form of modeling. We collected 4,079 pixels identifications for our machine learning model, categorized in two classes, wallows and non-wallows. I identified by the red pixels on the right-hand side image, and the yellow pixels are the non-wallows. If this image also includes identifications of bison, they're the little black dots there. And the use of random forest also allowed us to better understand the accuracy found in our variables. This is a more of an in-depth identification of the pixels that we use. So we were pretty staunch in our use of pixels. Like if there had been more variation, then we don't believe that we would have gotten as good of a model quality. And this, if you go to the next picture, this kind of shows that the machine learning identifies the variables that perform the best. It wasn't acting as much of a black box, and it could show us where we needed to improve models or eliminate different variables. In the machine learning results, the spectral signature of objects matching wallows increased from 10 kilometers in 2021 when bison were reintroduced to 121 kilometers in 2023 and 129 kilometers in 2025. After post-processing, a machine learning for size and circularity of wallows, deep learning identified 379 wallows in 2023, and machine learning identified 222 for the same year. The deep learning model was able to detect a large number of potential wallows. However, it also produced a lot of false positives and often confused wallows for other features like roads, bare soil, and river edges. And this is applicable to the machine learning models as well. So it showed some potential that accuracy wasn't strong enough as needed for a reliable application, and to confer results that were not attributed to like a few number of pastures that we used for study. We also translated our results to 15 random sections of Fort Belknap bison program. And the figures that were returned in the results corresponded well to our existing values. The results for machine learning showed that the random forest model performed better overall. It had fewer false positives and achieved about 62 overlap with validated wallows at its best. It also was faster to run and required less computational effort. However, it still had some limitations, especially when applied across different years or locations where accuracy dropped. Even with those limitations, both models showed some consistent patterns. Most wallows were found in mixed grass prairie areas and clay-rich soils. And then another recommendation is just updating the models with the continuation to grow and progressively get better. Temporal resolution is improving a lot since now NAIP is offered year-to-year basis and at a higher resolution. And this suggests that bison may prefer certain types of environments for wallowing based on vegetation type and soil. And that could be useful for planning and restoration and habitat expansion in the future. The way that we fund this type of work at Bison and Pronghorn is through proposed legislation. So now I'll pass the mic to Maya to speak more about that.
Yeah, thank you so much, Gus. So I'll be talking a bit about funding opportunities for the North American Grasslands Conservation Act, and I'll explain why NAGCA, the abbreviation for the act, is particularly useful for Indigenous-led conservation and grassland conservation in general. And yeah, this is so the Great Plains are the biggest stretch of grasslands in the United States, as you can see on the map on this slide, but grasslands are also interspersed throughout the rest of the United States, admittedly in lower concentrations, but they're still there. So their conservation is really a matter of national importance, and a lot of Congress people have grasslands in their districts, so it should be really a matter of interest for a lot of Congress people as well. Specifically, grasslands occur in 35 of the 48 lower United States, so all the states except for Hawaii and Alaska but they're rapidly diminishing. 62% have vanished due to conversion to agricultural land like cropland, or industrial activity, and also encroachment by invasive species. And a lot of what's left is at very high risk of conversion because there's not federal protection of these grasslands. So there have been many efforts to combat grassland degradation, but recent one that I focused on is the North American Grasslands Conservation Act. It's a bipartisan bill that was introduced in the federal Congress in 2022 and 2024, and if passed, it would establish a flexible flexible grassland conservation grant program with a 10% set aside requirement for native-led projects. That piece is really important because in my gap analysis, I found that a lot of existing federal conservation acts strongly disfavored native-led conservation by focusing on traditionally croplands, and actually some streams of funding did not apply to Native nations at all. So the set aside is a really important step. So my main research question, given how effective NAGCA could be, is how can we maximize NAGCA's appeal to policymakers and also its uptake by conservation groups if it is passed? And the methods I used to examine this are, I looked at economic contributions to grasslands. That piece was important because that could be used to argue that NAGCA is federally very beneficial. I also looked at existing federal grassland conservation acts through kind of a gap analysis lens to see where these acts have fallen short and how that can be remedied through NAGCA. I also conducted some on-the-ground conservations with people from the Rocky Boys Bison Project, which was very helpful for informing these recommendations. And I also developed a tool in Python that suggests a financing strategy for NAGCA. And then finally, I used Freedom of Information Act requests to determine where previous funding had gone to from existing conservation acts. So to begin, the financing strategy I developed is basically to just increase the federal grazing rate until it reaches $7.97 per animal unit month. So for context, I'm sure most people in this call know this, but animal unit month is the amount of forage required to feed a cow and her unweaned calf for a month. And it's currently, the grazing rate is at $1.35 per month, which is very low. It was established, this program where ranchers can graze on public land was established in 1981 with a rate of $2.31. And even though inflation has gone up since then, the grazing rate has actually decreased. In this graph, you can see it has fluctuated a lot over time, but the green trend line shows an overall decrease over time. So a lot of groups have actually argued that this has heavily subsidized grazing, which has led to a lot of overgrazing, which is a threat to grassland and the habitats it supports. So a lot of groups have actually argued for increase, including some ranchers, because they see that it's important for the longevity of their careers. So in this graph, there are a few rate increase scenarios. So the $7.64 was suggested by the Center for Biodiversity and a coalition of other conservation groups, and they actually took the federal government to court over this. It was not successful, but it shows that there are a lot of people dedicated to increasing this federal grazing rate. The $7.97 fee is what would be required to completely finance NAGCA, and then the $8.61 is, as I mentioned earlier, the initial grazing fee was $2.31 in 1981. So if inflation were taken into account, $8.61 is what it would be today. One limitation is there's an executive order put out, I think in 1986, says that the federal grazing rate can't increase by more than 25% each year, or actually can't change by more than 25% each year. So applying that cap, we're looking at a 25% increase every year, and that's shown in that table in the bottom. So year zero is basically now. The 135 might change depending. The BLM and USDA put out new grazing fees every year. It's been 135 for the past few years, but it is subject to change, so that would have to be updated. But this shows a scenario based on the current rate, and it would take 9 years to increase to 797. Other recommendations are to do with, if NAGCA does get passed, how it can be modified to facilitate maximal uptake by conservation groups. So the first recommendation is to create a set of standardized metrics for grassland performance. This is important because NAGCA would have to be reauthorized every 5 or so years, and if there's data backing its effectiveness, there's a lot more of an argument that could be made in its favor in Congress. A lot of conservation groups have actually talked about how there's not enough federal metrics for grassland performance. So that's really important. And the metrics that Bridget talked about for pronghorn connectivity can be standardized for other species and other habitats to be applicable to federal projects. So that is a possible starting point that could be very helpful there. And the second recommendation is to reduce barriers to participation by simplifying the grant application process. A lot of existing bills have come with a lot of burdens for especially, I mean, anyone who's applying to these grants is already doing a lot of work. So farmers, ranchers, Native nations all have very full schedules, so they don't have a lot of time to be applying to these grants, and that has posed a barrier to a lot of potential participants who then are not able to spend that time applying to grants or actually to afford application fees. So NAGCA would establish regional councils, and they could be mobilized to apply free or low-cost consultation to applicants, because applicants already do a lot of outreach with private consulting firms, which can be pretty expensive, which limits the people that can apply to these programs. And then a few avenues for further work that could be that could strengthen this research. So firstly, the rate increase I'm proposing is pretty drastic, even though it would happen over time. We've never seen a grazing fee this high. So to avoid even though there are ranchers that support this, there's probably going to be some that don't. There's definitely going to be some that don't. And if they're powerful enough, this can prevent NAGCA from being passed. So we might want to look at diversifying the funding stack for NAGCA. There's one option I was looking at, which is the government has been more recently leasing public land for renewable energy production. And we don't necessarily want to increase the rate at which this happens, because we don't want to fully disincentivize renewable energy production unless it's being done in an unethical way, which is true a lot of the time, but that's a topic for another conversation. But in order to avoid increasing these rates, there's already some set aside of this funding for conservation. So we would need to understand how the government uses this funding and if there's any that could be applied toward financing NAGCA. Secondly, I also recognize that the increased grazing fee would potentially or likely cause problems for lower income grazing operators. There was a study that showed that a lot of the land that's leased from the federal government is by large scale operators, so they should definitely be subject to the higher grazing fee, because with economies of scale, they're able to just basically snatch up a lot of this land and overgraze on it to their heart's content. But there are a lot of people for whom the low grazing fee is important, because private grazing fees are much more expensive. So I think the Python code that I provided could possibly be modified to have some kind of graduated rate depending on operation size or income, so that smaller operators would not be harmed by this rate increase. And then finally, I already talked about this a little bit, but some of the metrics that Bridget introduced in the habitat suitability section, as well as Lou's literature review and Mary's ground truthing pieces, could be standardized to apply to more species and grassland ecosystems. And these could be, if there's uptake for these, they could be used to report on NAGCA's effectiveness. So now I think Mary will talk about our overarching take-homes.
Yeah, I'll just really quickly kind of wrap things up so we have time for questions. But a few take-homes that we have, sort of the first one's kind of a personal one, which is that throughout this whole process, BNGA has really set the direction of the project, like what the like the proposal that they submitted initially and all these other goals and our role as CES students and non-Indigenous students has been to really try and support their vision as best we can with requested skills and resources that we have here at U of M. And the second one is kind of more broad, which is that Native nations have stewarded these grassland ecosystems for thousands of years and will continue to play a prominent role in the grassland conservation space. And so, in this kind of Indigenous-led stewardship that we're supporting here. So that stewardship supported by sustained public investment, like NAGCA, like Maya mentioned, can really help to strengthen the future of grasslands in the NGP ecoregion, and ensure that these ecosystems remain for generations to come. So thank you so much, and we will open it up for questions. Oh, yeah, Sean, go ahead.
Hey everybody, long time no see. Just wanted to say that excellent work. I thought you guys did a really, really good job.